right, good morning, everybody. I'm actually switching my topics from the 10-minute talk to the half hour, so I've swapped this out. So this talk is actually about 128-bit versus 256-bit. And actually, I had this conversation last night, and I asked one of the people at the table, is AES, is it 128 or is it 256-bit? And everyone at the table struggled to come up with the answers, whether it was 128 or 256. So it gave me further verification that this may be a valuable talk for you guys this morning. Okay, so this talk is going to dive into the depths of whether we're using 128 or 256, the advantages of each, what happens in reality, what you guys can expect. Okay. There we go. Okay. So way back in the days, if you imagine the times in the ancient Romans, you'd have individuals like Julius Caesar who had a fair bit of secrets that he needed to keep from his peers, from his lovers, from the people underneath him. So he'd send messages, and he'd need to encrypt or encode these messages so that other people couldn't decipher what the messages were. So he came up with a cipher, and we'll dive into the depths of the cipher, but it's known now as the Ceasar Cipher. Okay, which is basically a rotational cipher where you'd rotate letters of the alphabet to encrypt the message that you were sending. So back in Caesar's day, just rotating the characters was enough to introduce enough complexity where people weren't able to decrypt the message that was being sent. You also have messages in 1934, the Ovaltine Company sponsored a radio show in the US, the Little Orphan Annie. And if you signed up for the fan club, the Little Orphan Annie, they sent you a fan club book. And in the book, it gave you the code so that you could rotate characters of a message and start encrypting your message. Also in cereal boxes, right? You get the Captain Midnight ring. The Captain Midnight ring would allow you to encrypt. You'd spin a dial on that ring and you can encrypt messages. So kids that were 4 or 5 years old were encrypting messages and exchanging messages between each other so that their parents weren't able to figure out what messages they were sending to each other. Okay, so there's a long history in this. Okay, so just a little example of the Ceasar Cipher. If we encrypt the message, if we have a plain text message called WLPC for the win, if that's our plain text message, and we do a rotational 4 code, so basically we're rotating characters by 4 in the alphabet. That message would look like this. Okay, so if we sent that message out, these characters would basically look like jargon. But if we knew that we were doing a ROT14 code, we'd be able to decipher that back to WLPC for the win. Okay. If we did a ROT13, which was a common Ceasar cipher, basically you're rotating characters by 13 characters, you get this message. So it's different than the ROT4, and you'd have to know how many characters you're rotating it by. So as long as the transmitter and the receiver knew how far to offset the characters, you'd be able to recover the original message. Now, ROT26 sounds even better. Okay? It sounds like better even coding, right? So sometimes more isn't always better. Right? If you do a ROT26, basically you've blown your encryption, okay, and you're sending the exact same message. Okay, so be careful. Sometimes more is not always better. Okay, so just a little bit about me. Again, I'm Troy Martin. I bought my first wireless NIC in 2001. Some people talk about when they bought their first computer. I like to start with when did you buy your first wireless NIC? So ever since then, I've been hooked on Wi-Fi. I cut my teeth kind of in the networking industry and working in the carrier space. So I worked in the telecom space before making the dive into Wi-Fi full time. I worked in the industrial space for a long time, but I worked in a refinery. There was an explosion. People were evacuated. 2 guys got sent to the hospital. They ended up having 3rd-degree burns while I was doing the site survey walkthrough. I decided industrial Wi-Fi wasn't for me. You know, I like my family. I wanted to see them again, so I decided to do more carpeted-based Wi-Fi. Okay, so a little bit of what this talk is about. Okay, I'm not going to dive into the depths of WEP. I don't care about it. From my perspective, WEP doesn't exist anymore. WPA and TKIP In my mind, that doesn't exist anymore. I'm going to talk about WPA2. So I know there was a talk yesterday. Perry and Philip gave a talk about WPA3. But WPA2 will still be around for some time yet. So my talk today is specifically going to focus around WPA2. And of course, you've already had some talks about WPA3. Right? So I don't need to go into the depths of that. Okay? But why this talk? Okay? I still see RFPs come out. We have customers that are asking in their requirements, they're asking for AES 256. Okay, specific requirements. We ask them what devices they're connecting. They're like, oh, we want every device to connect. We want them all to connect. I'm like, but really one of your defining requirements, AES 256. Let's talk and explore that. How many characters are available in the passphrase? When you guys type in your passphrase, how many characters can it be? Do you guys know the answer to that? Okay. The PSK itself, is it a 256-bit key passphrase or PSK? Or is it 128? Or is it 192? Okay. The block size, when you encrypt AES, are you looking at 192, 128, or 256? Okay. If you guys know the answer to that, great. You're better than the table we were at last night. But okay. So a little bit on an encryption primer. Okay, so there's a few concepts that are required in encryption. So one of them is obfuscation. Okay, and that's making the password difficult to understand. So if you look at that Ceasar Cipher that we had, setting things to be the ROT4, ROT13, and you move the character around, it makes it a little bit difficult to understand if you initially look at the password. All right, but there's some things that I'll show you later that can make it more obvious what type of encryption that you're using. Okay, so one goal of encryption is to obfuscate the data. Okay, another thing is if you inject a key or your cipher, you want to make it that when you're changing one character, it has an impact on multiple characters. So you're making multiple changes to the plain text. Okay, so the more change, the better your cipher is. Okay, you want to make it confusing. Okay. The person looking at the key, you want them to make it appear that it looks like random characters, random text, random jargon. So if you're doing a packet capture and you're looking at packets going across the airwaves, which we can all see, you want to make it look like gibberish to the users. Okay? The more gibberish looking it is, the better off your cipher is. Okay? And you also want a certain degree of entropy, which was like it's a measure of randomness. Okay? The more random looking the characters are, the better off your encryption cipher is. Okay, so basically, the concept of encryption is you inject plain text, right, which is the message that you want to send. You add some sort of secret key, right, that ideally is unique between yourself and the person that you're sending the message to. You apply some super complicated cipher that's mathematically impressive to other people, but complicated enough that they can't resolve, and the output is your cipher text. Okay, or you just mix it through a discombobulator and everything becomes easy. Okay, so a little bit about the entropy and the confusion. Okay, this is a little graph that represents characters that show up in the English language. Basically, if you graph the number of times certain characters show up, more characters are more likely than other characters, right? So if I'm just offsetting the characters by a ROT4 or a ROT13, and I apply this graph, certain characters will show up more. And so if I've only done a character rotation and I apply this graph of how many times the letter X shows up and it matches where my E is, well, I can take a reasonable guess that, hey, I've just rotated my characters off by a certain amount. Okay, so I haven't met the entropy expectation of encryption. Okay, I haven't provided enough randomness in my graph. So you can do some analytics on the messages that you receive to see if they show up and match this graph. Okay, so we're going to go through a little bit. If you guys have taken any CWSP training, which I don't think the class was offered here this year, the CWSP. So we'll do just a little bit of baselining for the passphrase matching. So basically, to create the passphrase, so this is when you enter your passphrase, whenever you connect to a wireless network or your secret key. Basically what happens is we run through an algorithm that converts that to a bunch of characters. And so we leverage the passphrase, the SSID, we take the SSID length, we hash it 4,096 times. right? So instead of doing like ROT4, ROT13, ROT26, we just run it through the calculation 4,096 times, and the output is 256 bits. Okay, so the last number is how big I want this key to be. So when we convert the passphrase to a PSK, it ends up being 256 bits. Okay, so here we have 256, but this is not the key that we use to actually encrypt the data. Okay, so the key itself, when I asked those questions earlier, how long is the PSK? If you guys knew, great. If you didn't, it has to be somewhere between 8 and 63 characters. Okay, so the IEEE and the Wi-Fi Alliance both recommend that these passphrases are at least 20 characters. Right, so that makes it resilient to brute force attacks, dictionary attacks. But if you make your key at least 20 characters, you should have a key complex enough in today's time that's resilient based on computational time of today's technology to be relatively secure from dictionary attacks. Okay, but you have to judge and mitigate your risk based on what your users are doing. If you give everybody a 20-character password, that may be complex for hotel guests, for example. If they have to type in a 20-character password that's a mix of letters, numbers, and special characters, and they have to enter that key every 24 hours, because you have your ridiculous policy at your hotel, that could be a big burden. Right? If you're at a school and you want your parents that are showing up to watch, the basketball game, the volleyball game, the football game of their children, when they show up, if you want them to enter 20 characters, that may be asking too much. People can confuse L's and ones and I's, capital I's. They can be confusing O's and zeros. So maybe if they're only given 24 hours access, maybe 8 characters, all digits, may be reasonable if all they have access to is the internet. Right? And then on the back end, you're creating firewalls. You're limiting the access of what they have with regards to content. Maybe 8 characters is enough to mitigate the risk. Okay, so when you're choosing your passwords, look at your users. Decide how complex your password needs to be to mitigate the risk. Okay, some of the schools that I've worked with, we've actually found that we could give more complex passwords to students and less complex passwords to the teachers because they had troubles typing in the characters. Okay. Also, the available characters for the password need to be in the ASCII range between 32 and 126. And so I have a slide that'll explain this in a little bit detail. Okay. And of course, the SSID length is just the number of octets. We're running through this hash 4,096 times, and the output, again, is 256. Okay, so here's where I think some of the confusion comes from, is that you see 256 bits. Here's an ASCII slide. So we have the characters number 32 through 126. So basically the second column and all the way until the last line on the far right. The first column is not available for characters. But I'll remind you, if you guys were paying attention yesterday, if you look at number 42, it does map to that asterisk. It depends for the ASCII value. But this is just a reference for you guys to see what characters are available. Obviously, it doesn't make sense to enter like a backspace or delete. This slide is also for reference, just to put some context around. So yesterday I talked about the MSDU would be 2304 bytes in length. That does not include any of the encryption header. So if you're using WPA2, that adds an additional 16 bytes of overhead to that frame. Okay, so it extends beyond the 2304 for the frame bytes, which reduces your efficiency. Okay, but this is just an idea. This is specific to the WPA2 if you're leveraging the RSN. Okay, and if we do a packet capture, and we look specifically at these frames, okay, we'll see that they're encoded and they're using the 000FAC, or the Alpha Charlie, which is an identifier that they're using the RSN security element. But if we look even further, because they're encoded with 04, and this is really the key that you see. This is a table from the IEEE documentation. When it's coded with 04, that maps up to the CCMP 128. Right, so this is the ultimate answer to this presentation. We're looking at 128-bit encryption. Okay, and that's contained within the frames. If you map this out to the chart, we're looking at CCMP 128. So if you do a packet capture in the bulk of any encrypted traffic on your network that's leveraging WPA2, it is coded to use CCMP 128. In order to support 256-bit encryption, you do need customized software on your client. right? And you need the AP that's able to negotiate that capability between your clients to exchange that information. But the bulk of traffic, by far, is sent using CCNP 128. This was talked a little bit about yesterday, so I just have this up as a reference, just for the four-way handshake. Basically, that's the conversion from the PMK to the pairwise transient key, right? So it's exchange of information between the authenticator and the station, okay, with some A nonces and some S nonces. So the authenticator nonce, supplicant nonce, exchanging some of that secret information. But basically, that's able to generate the PTK after the four-way handshake. All right, so let's walk through this process a little bit. If I enter a passphrase, right, I mentioned it was 8 to 63 characters. Okay, so I can type that in, any combination of that. Obviously, the more secure you want to be, the more risk you want to mitigate. You want to make the password more complex, go in anywhere up to 63 characters. Okay, those 63 characters end up getting converted into a pre-shared key. Okay, so we have to run through an algorithm to kind of scramble up those characters and convert into a pre-shared key. That pre-shared key ends up being 256 bits. And the pre-shared key in its 256-bit form is equivalent to your PMK. Okay, so we have a bunch of basic acronym collisions here that happen. Okay, and the PMK via the four-way handshake is converted to your PTK, which ends up being 512 bits. Okay? But you also, instead of entering your pre-shared key, if you have rare, clever individuals, you could directly enter your password in hex. Okay? If you enter it in hex, it needs to be 64 characters. And this is the differentiation so that the software knows, am I entering the password in hex, or if I entered just characters that are less than 64 characters. So if it's exactly 64 characters you've entered in hex, that hex value directly becomes your PSK. Because 64 characters in hex is 256 bits. Okay, whereas your passphrase could be anywhere between 64 and 504 bits, right? The character is converted into bits. So now your PSK in this scenario directly becomes your PSK, or sorry, your PMK, which is 256 bits. And then through the four-way handshake, you can drive your PTK of 512 bits. But you could also come in via 802.1x. Okay, so if you come through 802.1x, the result of your authentication in 802.1x is something called the AAA key. Now, the AAA key, depending on the authentication method you use and the operating system that you use, it could be a wildly long set of characters. But the AAA key can be converted to your MSK, your master session key. And we just take the first 256 bytes, or sorry, 256 bits of your master session key, okay, and that becomes your PSK, which is also your PMK, which then via the four-way handshake becomes your pairwise transient key. Okay, so we have a bunch of different mechanisms to drive these key bits, okay, these values. Okay. All right, so here's just a slide that kind of summarizes all those different ways that you can connect to your network. So once you have your 512-bit PTK that you drive through your four-way handshake, now you can drive 5 more values, okay? And these 5 more values are split up in different various 128-bit values and 64-bit values. And so I break this down over here. You have that key confirmation key, right, which is just used to encrypt additional data that you're sending between your client. You have your key encryption key, which is used for your mix. Now it's your temporal key. That's the important key, which is another key that's only 120 bits in length. So the temporal key, that's the key that's important. So that whole process is to drive the temporal key. You also have up with 2 MIC keys, but as I talked about, that's only relevant to TKIP, so I don't care about those. Okay? And so this slide, taken from the CWSP guide, that whole process was to generate this 128-bit key that you use for the encryption process. Right? So now that we know that it's 128 bits that we're using for a key, let's talk a little about AES. Okay, what's the mechanism that AES uses to encrypt traffic? Okay, so again, for AES Design, we have our plain text input coming in, and so we have to chop the data that we want to encrypt into 128-bit blocks. Right, so we carve up that data, segment it. So if we're sending a 1500 byte frame, we chop it up into 128 bits, encrypt that, and then the next block, and the next block, and so on and so forth. Okay, we add our 128-bit key which is our super secret key, and we apply some complex cipher to it, and out comes our 128-bit block. Okay, then we do the next block, and the next block, and the next block. Okay? So the AES encryption process itself, because we're using AES, we're going to go through 10 rounds of this encryption. So we start off with the state, and the state is basically a reference for each stage in the table of where our data is at. Okay, so we do initial data coming in, we do some manipulation, we call that the state, we move to the next step, we call that the state, move to the next step, we call that the state. But with AES 128, we go through this 10 times. If you went through 256-bit encryption, you'd go through this process 14 times. Okay, so instead of like doing a ROT 4, you do a ROT 13. You just go through it more iterations. Okay, but one comment on the final step. So for 128-bit for stage 10, we do not apply the MixColumns step. Okay, so that changes as we get to the end. Okay, so we're going to walk through this process for AES. But just to kind of set the stage, there's 4 transformations that we need to go through. Right, so a substitution, shift rows. We're going to mix the rows. And then we're going to apply the encryption key that changes for every stage. Okay, so it's a new encryption key that gets modified and created for each stage, which is a completely separate process for generating that encryption key. Okay, so here's our state. This is the text that we're trying to encrypt. This is where it starts off. This is what it looks like. Okay, the first step is the substitution bytes. Okay, in the substitution bytes, we take a substitution block, and basically it's a portion of the Rheingel infinite field. Which has been expanded to a 256-bit chart. It's a static chart. But basically what we do is we take this first byte. So we write this as, it's a 16 by 16 grid, where we're taking 16 bytes, so 4 bytes in each row, or 128 bits. We take the first byte, so it's 19. And we split this into an upper nibble and a lower nibble. Okay, so the upper nibble is the 1, the lower nibble is the 9. And so based on that, we can do a lookup. So the upper nibble gives us our row number. The lower nibble gives us our column number. So we can match this up in the grid. And so 19 gets converted to delta 4, or D4, right? So we figure out what the substitution is, and then we just pop that into the table, right? So we do our substitution. Then we take the next byte, okay, which is our 3 delta. We look it up in the table, find out where the row and the column is, and we swap that out, and it ends up being 27, and so we just switch that out. And we keep doing that through the entire state. Okay, for each byte, we move it through, okay, swapping it out, okay, and then we can expand this out, do this a little faster, we go column by column, and that's the substitution step. Okay, so that's what happens in that stage. The next stage is the shift row stage. Okay, and shift rows, basically you're moving the bytes based on the row that you're in. So the first row, there is no change. Okay, it's row 0, we don't make a change. In row 1, we shift the bytes by 1 to the left. Okay, in the second row, we shift by 2 bytes to the left. In the third row, we shift by 3 bytes to the left. So we offset the rows. Okay, add a little bit more complexity. Okay, in the MixColumns, this is where in 1949, Claude Shannon, who is the father of encryption, he wrote a paper where he identified the property of diffusion. The MixColumns is where we introduce diffusion into this algorithm, right? So what we do is we take each column and we multiply it by a matrix. And this allows us to make multiple changes to each of the characters within the state. So when we multiply it by this matrix, this is the output we get. So you multiply this out through each of the columns, which again scrambles more of the states. So we can go through that. Okay, and then the final stage, it's the AddRoundKey, or the whitening. Okay, in this stage, we take a key value and we take a column, the first column from our current state and the column from the key value, and we do an XOR function of each of those. Right, so we XOR that and we get this output. Okay, and that's how we figure out what our first column is. And we do the same thing with the next column, and the next column, and the final column. Right, so we add this key whitening. Okay, and that's it. Now we finished round 1. Okay, so we do this 8 more times, and then the last time we do the same steps except for the MixColumn steps. Okay, so I'll just let you guys your minds run through that. But let's talk about that key expansion. Okay, so the key expansion. This is our encryption key. we have to modify that. So here's our encryption key, and the process for the key expansion is come up with that 4-stage of the AES process. We have to have 10 modifications of that. So for the modifications, we take the final column, okay, we rotate the words, right? So basically we take the bottom byte, we move it up to the top. Okay, and then we do the substitution byte. So again, we use that the Rangel infinite field. We substitute the bytes for each of these fields. So we swap those out. Okay, and then we take the first column and we XOR that with our modified bits, and we take the archon table. So we take, because it's the first step of the stage of the table, we take the first column of the archon charts and we XOR that. And that gives us our final answer, which ends up being the first column of the key field. Okay, now we can cheat a little bit and save some time. We just do some XORs of that first column with the second column of the original key, XOR that. We do the similar thing for the second and third column and the fourth column. And now we have our key for the whitening step, or the AddRoundKey. We have that key that we use in the previous step. Then we keep running through this process, because we have to expand this key out a whole bunch of times. So we go through the same iterations, go through the archon steps, and eventually we get to the key 1s, key 2s, key 3s, all the way up to key 10s. Right? So now we can generate our randomized key values based on our encryption key coming in. So we're never actually using the cipher key coming in. It's expansions of that key that we're using to encrypt the data itself. Okay? Okay, so if we look to expand this out globally, in round 2, we go through each of these steps. At the bottom, the state table is what the values look like. And then we run through that calculation again for round 3 and again for round 4. We go through round 5 and round 6. Okay, we keep going, all the way up to round 9. Okay, remember in round 10, we do not have the mixed column step. So the final round, whether you're doing 128, 192, or 256, does not include the round key step. But finally, at the bottom, we get the encrypted text. Okay, so that's our 128 block. Now we go through the same exercise for the next 128 bits. Okay, and this is how we encrypt our data as it's going through the wire, over the airwaves. Okay. Now here's just a little bit of insight into the hardware coding requirements for your software. Right, you can do some pre-computation, or you can just generate everything on the fly, right? So that S table, for example, you can pre-calculate that and have that table as a reference. So now as bits come in, you can just reference that table instead of calculating everything on the fly. So if you're doing no compute, it's relatively small code size, right? So you have a small code footprint, but it takes a lot of calculation time, a lot of resources, right? So if you're an access point, you have a lot of memory, maybe you can do some pre-computation, have these tables generated, so you can start encrypting traffic really quickly on the fly. But if you're a watch or an IoT device, you don't have a lot of memory, maybe you're not able to generate these tables ahead of time and keep them stored, right? So here's just a table that walks through that process. If you guys have taken the Python class from Jake, and you guys have got your programming on, your closet programmers, and want to get excited about this, you can go to this website here. There's a bunch of coding references, regardless of your language of choice. You can look at these references, and basically this is source code on how you can write the AES encryption protocol. So you can analyze that, review that, dream about that at night if you want to do that. Okay, but more specifically for the audience here, because you guys are Wi-Fi people, you can look at the source code for the WPA supplicant. You can review that and look what's happened. So this is most of the Linux software platforms that use this. It's embedded into a lot of access points to leverage the software as well. But you can read the source code of exactly how this process works, and you can look through that. So if you haven't had a chance, I highly recommend you sign up for the Python coding class. It's fantastic. Jake does a really good job of walking you through that class. But you also have some documentation on this, so you're not being thrown into the wolves. Okay. Respect to additional information. If you haven't already read the white paper from Devin Aiken, where he explains the golden chickens and the white eggs, if you haven't had the luxury of reading that paper, I highly recommend that you go read that. Or purchase a copy of the CWSP book. Okay, it's a fantastic resource written by the two Davids, so you can purchase that book. And with that, that's the end of my presentation, so I'm going to disassociate from you guys now.
Merci.